Good morning. Today we're going to go over two very major vector, not applications, but basically vector invented operations. Let's say it that way. Vectors can be added, vectors can be multiplied by scalars. That's the only natural operations that can be performed on a vector. Vectors cannot show up in a function. You know, I can't have like the cosine of a vector. I can't raise a vector to a power. I can't have a quotient of vectors. It's very limiting. But we have created and defined operations with vectors. The analogy I'll use is if anybody here has had linear algebra, or you remember anything about matrix theory, matrices are essentially the same in that you can add them and you can multiply them by scalars if they're the appropriate size. But we defined an operation called matrix multiplication. And then we define it and it's consistent and we use it. Well, we're going to define two different ways to multiply vectors, okay? Because that's not a natural operation, so we have to invent it, and that's the way it's going to start. So the first one is called the dot product. And again, most of you are familiar with this. Now, when it comes to vectors, dot product is by far the most commonly used. It's not even close. In mathematics, this is 99 point thrown about 109% of the time. The second one we're going to use is what's called cross product. In mathematics, cross product isn't used ever. It's only used in calculus 3 and physics, but in the rest of mathematics, you will never see it again the rest of your life if you studied math forever, but you will see dot product a bazillion more times. But in Calc 3, strangely enough, cross product is the one we probably use more often. So we're going to learn both because they're very different, and the types of results we get are quite different. Now, dot product, okay, I'm going to define it in general, okay? So let U and V be in Rn. I have two vectors that are the same dimension. Now, in our course here, we're only going to use 2- and 3-dimensional vectors. But what I'm going to define is true in all dimensions. There's no exception. So we'd like to know what's the general rule, and then we can say, what are we going to use in our class? So is U1, U2, Un. Vector V is V1, V2, Vn. And we're now going to define U dot V. U dot V is defined to be the sum from I equal 1 to n of Ui, Vi. That's it. That's the formal definition. And by the way, I'm going to go back to the statement here. U and V are in Rn. What that means is all of the elements, U1, U2, and so on, they are all real numbers. That's extremely important in this definition. Those who've had linear algebra, particularly if you were in my class, you understand that we also talk about vectors in the complex realm. So if the elements of my vectors are complex, the definition of dot product actually has to be tweaked slightly, okay? But for real valued vectors that we're using here, this is the definition for dot product. So if I expand this, what exactly does this mean? Well, let's see. When I is 1, it would be U1, V1. Summation, so plus U2, V2, plus all the way to UN, Vn, okay? So this is how you do a dot product. I multiply these two guys plus the product of these two plus all the way down the line plus, which means that dot product is a scalar. It is not a vector. And that's really important to recognize that. Dot product produces a scalar. This is a single number. Now, because the U's and the V's individually are real numbers, then is it true that this equals V1U1 plus V2U2 plus VNUN? Yeah, because real number multiplication is commutative. But notice this would therefore be V dot U. Aha. This is a good thing. Yesterday or last day, we proved that vector addition was commutative. Turns out for real valued vectors, dot product is commutative. Okay, that's a powerful thing. U dot V is equal to V dot U in this context. And in both cases, they simply produce a scalar. So let's do an example. If vector U is 3, -8, 4, vector V is -2, 1, 3. Then U dot V -6 plus -8 plus 12. And that would be -2. Dot product can be positive, it can be negative, it can be 0. There's no restriction on the value you're going to get with dot product. That's pretty simple. Now, that's easy, but what the heck would we ever use that for? And that really is the question. So if dot product is simply a way of getting a scalar value between two vectors in the same dimension, it has to have some physical meaning. And so that's what we're going to discover next. Okay, I'm going to go ahead and erase this. Now remember, the lectures are recorded, so if you don't take great notes, that's okay. Also, in the module section, you will see notes on dot product and on cross product. So you can actually get more information just by, if you have those things. If you want to print those out or just leave them on Canvas, there's more information there and detailed. So now let me go over something that hopefully all of you remember from basic trigonometry. Okay. There's a relationship between A, B, C, and theta in any triangle. Does anybody remember what it is? There's a formula here. It's probably a little bit obscure. So C squared equals A squared plus B squared minus 2AB cos theta. Now, I would hope all of you have done this sometime in your life, probably not recently. Does anybody know what this is called, this formula?
Law of cosines?
Law of cosines, good. Law of cosines is very powerful. Now, the law of cosines applies to all triangles. So what if theta ends up being a right angle? What if this was actually a right angle? Then what is this term?
0.
0, and then you have the Pythagorean theorem. So the Pythagorean theorem is a special case of the law of cosines. Okay, cool. So why are you showing us this, Mr. Brown? All right, let's suppose I have vector u and I have vector v. Okay, and they have an angle of theta between them. And I'm drawing a two-dimensional picture, but what I'm doing, it will be true actually in all dimensions. I can have two vectors in 3 dimensions with an angle between them. I can have vectors in any dimension, and there will still be an angle between them. It's harder to visualize. Now, what if I want that? Now, here's what I'd like to do. I would like to take the vector v and turn it around. Okay, if I took the vector v and I turned it around, and then I added it to the end of vector u. So let me pick up vector v, and I'm going to turn it around, and I'm going to add it to vector u. Okay, so if I added negative of vector v to vector u, I would get that, wouldn't I? That guy right there, which is the same as that guy right there. So this vector here, right here, this vector is vector u minus vector v. And again, it's easy to see it because if I simply take the negative of vector v and I add it to the end of vector u, I will get this result, which is exactly what that one looks like. So why is that important? Well, because in a sense, I form a triangle where the lengths of my triangle are not vectors. The length of this side is this. The length of this side is this, and the length of this side would be this. So I have exactly this situation created from these two vectors. So the length of this side is the magnitude of v, the magnitude of u, and the magnitude of the difference. Sometimes, by the way, this is named in many books. This is often written this way, d u comma v. We do this in linear algebra as well. This is sometimes referred to as the distance or the difference. D stands for both, the distance between two vectors. Okay, but in this picture, you notice I can use law of cosines. So to use law of cosines, what do I know? Then I know this quantity squared equals this quantity squared plus this quantity squared. So I'll write it as length u squared plus length v squared minus 2 length u, length v, cosine theta. Remember, these are all scalars. Okay, this statement here is absolutely true. This is true. This statement here is true actually in every dimension. If both of my vectors are in the 2 or 3 or 10, we're going to limit it to 2 and 3 in this class. But that is always a true statement. Now, in and of itself, it's not very helpful, not like that. So let's actually put values in for the vectors. I don't need this anymore. Okay, so if I said, I'm going to do the problem in 2 dimensions because it's easier to follow, but then I'm going to show it in 3 as well. So vector u is simply u1, u2, and vector v is simply v1, v2. Then vector u minus v is u1 minus v1, comma, u2 minus v2. Okay, so now let's put the numbers in. So what is the square of the magnitude? Well, remember, the magnitude is the sum of the squares of the components under a square root. So the square of the magnitude would just be the sum of the squares, right? There's no square root. So I'm going to take the sum of the squares. Now, that's got to equal the magnitude of u quantity squared, which would be u1 squared plus u2 squared, plus the magnitude of this, I'll come down a little bit, v1 squared plus v2 squared, minus 2, and I'm going to leave this in this form for now, because I don't want to write all the square roots. Okay, well, look on the left side, look what we have. We'd have u1 squared minus 2u1 v1 plus v1 squared plus u2 squared minus 2u2 v2 plus v2 squared. This is the left-hand side of the equal sign. This is the right-hand side of the equal sign. And you notice you see some of the same terms. So let's cancel them. So now my left side, all I have left is negative 2u1 v1 minus 2u2 v2. On the right-hand side, I have negative 2 times length u, length v, cos theta. Every term has a coefficient of negative 2. So if I just multiply both sides by negative a half, then my left side will simply read u1 v1 plus u2 v2. My right side will be length u, length v, cos theta. Beautiful. Now, let me go back to the beginning of the problem. What if these vectors were in R3? Okay, what if there was actually a third component? Well, my third component would be a u3 and it'd be a v3, which means when I squared it, I'd also have a u3 minus v3 quantity squared. I'm just going to put it up here for fun. Minus u3, or excuse me, plus u3 minus v3 quantity squared. But on the right-hand side, I'd also have a plus u3 squared plus v3 squared. So then when I expanded and canceled, these guys would still cancel, but I'd have an additional minus 2 u3 v3. And so down here, I'd have a plus u3 v3. This would still look the same.
Sorry, somebody's
Unmuted, taking over the screen.
I'm sorry?
Somebody's unmuted and keeps taking over the screen.
Oh, okay. Please mute yourself, guys. It's going to affect the video later on. Yeah, keep yourself muted. So what I'm pointing out is if these vectors were in R3, at this point of the game, all I'd have is an additional u3, v3 term. But why is that so important? Because what is this exactly? This is dot product. This is exactly the definition of dot product. Oh, and if my vectors were in R3, I said we had the one more term u3, v3, which is still dot product. So the left-hand side of this statement is u dot v. But the right-hand side is length u, length V cos theta. And this is the physical, practical, useful formula for dot product. I define dot product as being a sum of the products of each of the corresponding terms. That's the definition. But that in itself isn't very useful. This is extremely useful. And here's an easy way to think about this. If I have a set of axes, whether it's the XY or XYZ, and I'm in 3D, if I have a set of axes, then I generally write down vectors right in this form, right? 3, 5, 7. But when you go outside and you're out in the real world, I don't think you're going to see an XY plane and a Z axis when you go outside today. But I can still ask the question, all right, I have a vector that's a certain length pointing in this direction. I have a vector of another length pointing in this direction. No axes, just two vectors of a particular length in particular directions, and I'd like their dot product. Well, doing it in coordinate form is not very practical, but doing it using their magnitudes and the angle is very practical. So this is, think of it in coordinate form or in magnitude form. These are exactly the same thing. So this is the big result. This is not the definition. This is a result of the definition and the law of cosines. All right. All right, so let me erase this here, and let's keep using this because dot product is so incredibly practical and useful. Okay, so here's some of the things. Going back to this statement here, what if I was interested in the angle between two vectors? Well, it turns out that if the cosine of theta is simply u dotted with v over length u, length v, then to find the angle between two vectors, I just need to use inverse cosine. Great. We'll go a step further. What if? What if u and v are orthogonal? What does orthogonal mean, by the way, in this context?
Perpendicular.
Be perpendicular. Yeah. So why don't we just say perpendicular? Because perpendicular means you're orthogonal. Orthogonal does not mean you're perpendicular. Orthogonal is infinitely bigger and more wide-reaching. Perpendicular only applies between lines and planes. Perpendicular only applies if I can physically measure an angle between two things that are straight. Orthogonal doesn't matter what dimension you're in, and you don't even have to be straight. Orthogonal is way bigger than perpendicular. I'll give you a simple example. So we rarely use the word perpendicular in the math setting. We use orthogonal, but because vectors are straight, this would be the same as perpendicular. But it's not always the case. In fact, most of the time we use orthogonal, it won't have anything to do with planes or lines necessarily. I'm going to give you a simple picture. There's two words that people often confuse mathematically, and that's parallel and perpendicular. Because we were trained in remedial algebra to think of lines on the XY plane, and so parallel and perpendicular were very, very easy for us to understand. But you don't have to be straight to be either one. Now I'm going to do parallel first because we're going to use this also. Parallel, there are three properties for parallel. Okay. Non-intersecting, we know that one. Same direction, equidistant. If you're parallel, those three things apply, but you usually only have to show two of them. One of the mistakes people always make, if I say, tell me about parallel, you say, oh, non-intersecting. Okay. I'm drawing two lines here. Pick any line running along your ceiling and pick any line running along your floor. They're non-intersecting and they're absolutely not parallel. Okay, those are called skew. No, parallel is very special. Non-intersecting has nothing to do with parallel. Parallel or non-intersecting. But for every two lines that don't intersect, just keep rotating one of them. They still won't intersect, but they're not parallel. Parallel means they also have to be in the same direction. So I always tell people, think parallel, think railroad tracks. Think railroad tracks. They're always going in the same direction. They never intersect and they stay equidistant, because if the distance between them changed, that'd be hard on the trains. But can't they go around curves? When you get in your car and you drive on the freeway. Tell me about the lanes, right? The dotted lines. Tell me about the lanes. Are they non-intersecting? Hopefully, because if they were, we have a problem. Are they in the same direction? Yeah. And do the width of the lanes stay the same at all times? Yes. Are they always straight? No. So the lanes on a freeway are parallel. That's a perfect example of parallel. They're not straight, but they're non-intersecting, they're same direction, they're equidistant. Now, if you happen to be straight, it makes it easier. But the problem is we think of parallel as two lines on an XY plane, yet parallel applies in all dimensions. So we don't want to confuse. Now, perpendicular are lines and planes. It's just lines and planes or line segments, and they can be finite. Orthogonal. I have two curves right here. If I drew a good picture, these curves can be orthogonal. You cannot measure the angle between curves. You can only measure the angle between things that are straight, lines and planes. But if I drew the tangent lines, is it possible that my tangent lines are perpendicular? Yes, and if my tangent lines are perpendicular, then my curves are orthogonal. In Calc 2, you may have done orthogonal trajectories, which are very, very cool, but there's no straight, there are no lines, there are only curves. Another situation is, I want you to think of a basketball, right? Think of a sphere. Now think of the center of the sphere and go straight out the sphere, okay? Because what we're doing today is so important that we have a good picture in our brains, right? I've got a sphere here. I'll keep going. Now, from the center of the sphere, I want you to go right out through the sphere. If I went from the center of the sphere and I just kept going out, think like a ball pump. There's no angles made, but this should be orthogonal to the sphere. So how could it be orthogonal to the sphere? Okay, imagine you have a basketball in front of you, a beach ball, anything, and you grab a piece of cardboard, a flat piece of cardboard. If I touch the cardboard to the sphere, I don't want to mash it down. I just touch it. Technically, it only touches at one point. Right? I can mash it down, but I just want to touch at one point. Well, it turns out at the surface, that one point that it touches, it should form a right angle with that plane, and that's called a tangent plane. That piece of cardboard will be tangent to the surface of the sphere and will have to be orthogonal or perpendicular to that line. So this line being perpendicular to the plane makes it orthogonal to the sphere. See, that's why orthogonal is a more important word, because I don't have to be flat, I don't have to be straight, okay? But I was perpendicular to a tangent plane. So hopefully that picture will resonate in your head. I'm drawing a two-dimensional picture of a three-dimensional thing. Hopefully that makes some sense. So I want these words to be comfortable. So what if two vectors are orthogonal? Then tell me about the angle between them. If two vectors are orthogonal, then what about the angle between them?
It's a 90-degree angle.
90 degrees. So we say that u dot v in this case will be 0. So we actually have a test for orthogonality. We make this an if and only if. Two vectors are orthogonal if and only if their dot product is 0. Well, that makes it kind of convenient. Now, if my two vectors are in 2 dimensions, this makes it really simple. So I have vector u, let's say it's 4, 6, and vector v, I'll make it -3, 2. So u dotted with v in this case would be -12 plus 12 is 0. Check. The angle between these two vectors is 90 degrees. If I were to draw a simple illustration, 4, 6 would be something like this. -3, 2 would be about here, and I clearly have a right angle. Great, but that's in 2 dimensions. What if it's in 3? I don't think any of us can picture two vectors in 3 dimensions, just, in every which way, and then also try to picture whether they're orthogonal or not, but it's the same thing. So let me, different picture, or different circumstances. So what if vector u, smearing ink here. Vector u is vector ub, let's say 3, I'll make this not too bad. And this is 2, maybe -1, 2. Let's see. Make that. There we go. This will work. Okay, in this case, my u dot v is 6 - 4 - 2 or 0. But I can't picture or draw either one of these because they're in 3D, yet the angle between them would automatically be 0. Now, if we say vectors are orthogonal if and only if the dot product is 0, what if one of my vectors is the 0 vector? Is that a problem if one of my vectors is actually the 0 vector? Because what is the 0 vector geometrically? It's just the origin, isn't it? It's just that point. So if I took the 0 vector and I dotted it with another vector, won't I always get 0? What do you guys think? Will I always get 0 if I use the 0 vector and the dot product?
Yes.
Yes. But if we're saying, excuse me, orthogonal if and only if the dot product is 0, that would mean the 0 vector has to be orthogonal to all vectors. It is. The 0 vector is orthogonal to all vectors, which is interesting. So most of the time when we're talking about orthogonal and on, we don't want to use the 0 vector because yes, that's already there. We usually like to think of a non-zero vector, but the 0 vector is automatically orthogonal to all vectors because the dot product is 0. And you can measure the angle between them, and the angle between them would have to be 90 degrees in order to get that. Okay, so with that, okay, performing dot product is trivial. It's, arithmetic. It's not pre-algebra. It's significantly below pre-algebra in terms of the physical doing of it. You're just adding and multiplying numbers. What if the numbers are large? Well, use your calculator to add and multiply the numbers. That's always a simple thing. But after dot product, probably the most important vector property application that we ever use is something called projection. Now, again, if some of you have had linear algebra because you took things out of order, some of you are currently taking linear algebra, and many of you will have linear algebra next semester. We do spend a lot of time on the vectors. So projection is a huge one. Now, the easiest way to think of projection, I gave an example last day. Pushing the refrigerator across the room is an example. We think about things like that. You remember in Calc 2 work. So I'm going to give some examples like that. So I have a vector here. Let's call that vector u. And I have another vector, maybe right here. We'll call that vector v. Okay. I want to push a refrigerator across the room. And we know that work is simply the force multiplied by the distance. We know that. But technically, force is a vector, and so is the distance. And so dot product comes into here. So if I take the magnitude, how much force did I apply? How far did I push it? Piece of cake, right? I'm pushing it in this direction. I'm going that direction. Now, what if I'm pushing in this? I want to go in this direction, but I end up pushing it off in an angle. I want to push the refrigerator across the room, but I end up pushing it at a 45-degree angle. I can't simply multiply the magnitude of the force times the distance because I didn't push it all the way across the room. I pushed it something less than across the room. So imagine this way. I want to go in this direction, but I pushed it in this direction. I only get this much credit because that's how far I pushed it in this direction. Well, what is this? This is the projection of this onto here. And there's a theta in here somewhere. There's a dot product in there somewhere. I want to push the refrigerator across the room, and I end up pushing it completely sideways. How much of this did I get pushed across the room? None. 0. My projection would be the 0 vector. Nothing got pushed across the room because now my angle is 90 degrees. So projection involves dot product, and we'll see how in a moment. So here's the question I want. I would like to project V onto U. So I'd like to know how much of vector V is in the direction of vector U. So the first thing we do is, that's got to be a right angle there. Okay. Either it's all of it, or if V were orthogonal to U, it'd be none of it. This vector right here is the vector I'm interested in. That vector right there, that's the amount of V in the direction of U. So that vector right there is called the projection of V onto U. I could also do, by the way, the projection of U onto V, in which case I go dot, 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 dot. I'd go the other way, completely unrelated, different vector. I want this vector right here. Well, one thing I absolutely know is, won't this vector right here be a multiple of vector U since they're in the same direction? Does everybody agree that will be a multiple? Yeah. Now, exactly how long is this vector? What is this length? Well, this length is the magnitude of the projection of vector V onto vector U, right? The length of the vector is the magnitude. That's how long this is. I want this vector. Now, remember the example I used last day. I said, okay, I want you to go that way. Remember, that way is forever. And I want you to go 100 feet. So what we did was we took that way and made that way into a unit vector, and then took our unit vector and multiplied it by 100 feet. I want this vector. So the easiest way to do that is to take vector U, make it a unit vector, and maybe the unit vector is, this long, and then take that unit vector and multiply it by this scalar. So the answer to this question is going to be exactly the following. It's going to be the magnitude of the projection of V onto U multiplied by the unit vector in the direction of U. That's what we're going to get. Okay. Now, we don't know any of these quantities yet. Well, this one's actually easy. We know that one. But what's that one? How long is this? Does anybody see something there? Maybe very SOHCAHTOA-ish? What do you think? Is that a SOHCAHTOA kind of thing? That's a right triangle. I want that length. What is that length exactly? Well, what's the cosine of theta? Wouldn't the cosine of theta be this length divided by this length? Everybody? Yes? No?
Yes.
Maybe?
Yeah.
Yeah.
Yes.
So if the cosine of theta is this length, which is the projection, divided by this length, then this length must be length V times the cosine of theta, correct? Because we just said this divided by this equals this. That's SOHCAHTOA. That's the ka in SOHCAHTOA. Oh, so I now have something. I now know what that is. I now have the following. I have length V cos theta over length U. These are all scalars times vector U. This is my projection. That's exactly what it is. We just have a small problem here. I'm giving you vectors U and V. I'm giving them to you. But that means I have to calculate the cosine of theta. Ugh, that's a lot of work. I don't want to calculate the cosine of theta. And what if I just said, no, vector U goes that way this many units, vector V goes that way this many units, and here's the angle between them. What if I gave you U and V with their magnitudes and the angles, and I didn't give you coordinates? This would be even harder, perhaps. Boy, that numerator, that almost kind of looks like what? What does it almost look like? Anybody? The numerator? Or what is U dot V?
Dot product.
It almost looks like dot product, And what I like to do when I'm in my class is I like to distract people. And some of you have been there, and I'll say, "Hey, everyone, look over there. Everyone turn around and look in the other direction. I think it's Elvis." And I'll go like this. There. Now look, my numerator is the dot product. Except, can I do that? Is that legal? Can I just multiply the numerator by magnitude of U? Well, I can if I do what?
Do it to both
Multiply
sides.
both
Do
sides.
sides.
Not both sides.
To the denominator. Oh,
Denominator.
yeah,
There we
yeah,
go.
yeah.
Is that legal? That's totally legal. In fact, my numerator is now U dot V. What's my denominator? It's magnitude of u squared, which is exactly the same as u dot u. Remember, magnitude squared would be the exact same as dot producting a vector with itself. Do I have to know the angle between them anymore? No. This is actually a very simple process. That's the answer. That's the projection. Turns out, of all of the things you ever do with vectors, projection is probably the most common thing you'll ever do. And the example I just used a moment ago, talking about pushing the refrigerator across the room, we have to use a projection in order to answer the question. So it turns out, if I'm pushing the refrigerator completely sideways, well, then the dot product would have been 0. So I got nothing done, moving it across the room. So let's do an example of this. Okay, so let's suppose, and let's do it in 3D this time. I've got vector u is 2, 1, -3. I've got vector v is -4, 2, 1. I'll keep the numbers down. Now, here's what I'd like to do. I have a couple of questions I'm going to ask. This is really messy. I tried to clean my eraser today, and all it did was make it worse. Okay. I would like to find, let's go u dot v. Let's find theta, the angle between u and v. And let's do the projection. How about we do the projection this time of v onto u? It doesn't matter which way we go, but the formula, has to go with the right one. Well, let's start with u dot v. So what is u dot v? Well, that would be -8 + 2 - 3 or -9. Okay. Now, in order to find the angle, I need the magnitudes. Okay. That calculator here. I need the magnitude in order to find the angle. So the magnitude of u is 2 squared plus 1 squared plus the square of -3 under the root. That's root 14. The magnitude of v is 16 plus 4 plus 1 under the root. So that's root 21. So theta would be the inverse cosine of the dot product over these guys. Now, this is extremely important that we recognize this. My dot product was negative. Does anybody know what that means about my angle if my dot product is negative? Well, I know if dot product is 0, it's a 90-degree angle. What does it mean if my dot product is negative?
Is it greater than 90?
Yeah, it's obtuse. Oh, okay. Product, excuse me, positive dot product means you have an acute angle. Negative dot product means you have an obtuse angle. That's absolute. So now let's do this. My suggestion is put yourself in degree mode, because you're not going to use the angle in a calculation. You're using the angle to describe something. Okay, so let's do inverse cosine of -9 over root 14 root 21. Now, I got approximately 121.66 degrees. So that means I have an obtuse angle between them, which is evidenced by the negative dot product. It's important to recognize, if your dot product is negative, right, you're going to get an obtuse angle. The most common mistake people make in this is they'll get the supplement of this, right? 58.34 degrees. That's incorrect. That would be what I would have gotten if that were positive. Okay. You don't use sine to find the angle between vectors. You use cosine. If you use sine, you're going to get the wrong answer exactly half the time. Because if you use sine, you will only get acute angles back in. You won't ever get obtuse angles. Okay, so the last piece of the puzzle is the projection. Now, what do I need for the projection? Well, in this case, it's going to be u dot v over, now I'm projecting onto vector u. So it's going to be u dot u. If I did u onto v, then it would be v dot v. This guy here determines everything. This guy is the one that shows up everywhere. So u dotted with u would be 14. I know that from this statement. And then I'm going to multiply that by 2, 1, negative 3, which would therefore be, okay, negative 18/14, comma, negative 9/14, comma, positive 27/14. Always finish it. Now, question. I can reduce that fraction. That is correct. I can reduce the 1. I can't reduce the other 2. Should I? Does it matter? Am I better leaving it like this? And I don't know that the answer is obvious here. Anybody want to chime in? I can reduce that one only. Should I?
I would say keep the common denominator instead of reducing.
Probably a better idea, because very likely I'm going to use this vector to answer another question, and maybe I'm going to dot product with something else. If I end up reducing all my fractions and it produces multiple different denominators, that may make future steps more work. Now, what if all 3 of these had even numerators and all 3 of them could be reduced? Well, no, then you would reduce it. Everybody got that? The suggestion of saying, you know, in this scenario here, I'm probably better off doing this, just simply because I'm going to have to use it later. And having multiple denominators in my vector, that doesn't make it easier on me. Yes, it might be technically more simplified, but that doesn't necessarily make it a better answer. So what we've got now is we've got the definition of dot product, again, being the sum of the individual products. Great. Then we derive that the dot product also can be magnitude, cosine the angle. That's actually a more useful version. And then using that, we can come up with a projection of one vector onto another. Okay. Very, very powerful stuff. Okay, that's dot product. We're now going to then look at cross product, which actually has a little bit more going on. And we're going to spend a little longer on this one. Now, cross product is the one that people tend to have more trouble with, because I just showed you dot product. I showed you where it came from. It's very simple to see. I derived the projection, which is pure geometry, by the way. That was a geometric derivation. There was no calculus there. There was barely even algebra. But cross product, most human beings, including physics and instructors, have a definition. That's all they have. They have a definition of, this is the definition of cross product. In other words, in terms of a result, and just get it. And you're saying, okay, what does it mean? Where did it come from? Why do I care? Why is this necessary for me to know this? And then it turns out to be really important. And you go through all of these procedures and you do all of this algebra constantly, and you have no idea what the heck you're saying. I know this because I've been doing this for a long time, and I have never met a math or physics instructor who actually could tell you where cross product came from. They can tell you how to get the cross product, not where it came from. There's no origins. So several years ago, I think I'd been in linear algebra class. Students said, where does cross product come from? I mean, where did they just come up with this formula? I said, I don't know, let's figure it out. So we figured it out. Here's the point of cross product, okay? First of all, we have to be in 3 dimensions. Cross product is only defined in R3. That makes it very limited in scope, but it also makes it not abstract at all. Dot product is in every dimension. Okay, and so when we do rules of dot product, we give them generally, you know, for Rn. Cross product being only in R3 makes it a little bit easier in some cases, because I don't have to worry about 2 dimensions or 4 dimensions or 6. The point of cross product is I have 2 vectors in space. Here's my 2 vectors in space. The goal of cross product is to create a new vector. Remember, dot product is a scalar. To create a new vector that is orthogonal to both of the original 2 vectors at the same time. So I've got 3 vectors here where this one is orthogonal to these 2. So another way of saying it, if I give you any 2 vectors in space, any two vectors in space, they will uniquely determine, they don't form, they determine a plane. So I'm going to lay a piece of paper on these two vectors. There's only one direction this paper can go. Now, if I change this, now the paper's in a different direction. If I put the vectors here, now the paper's in a different direction. If I give you any two vectors in space, think of a big piece of cardboard and you're going to lay it across them. There's only one direction that piece of cardboard can go. So what I would like to do is to take my two vectors, and I'm going to create a third vector that's orthogonal to the plane that those two vectors live on. Okay, that sounds simple enough, but it's actually not that simple. Hang on 1 second. Hold on, everyone, just 1 second. I hear somebody yelling for me. Okay, I've got construction people downstairs and are hollering up to ask me a question. You know, should we knock down this wall or that wall? Yeah, well, maybe not quite that bad. Okay, let's consider I've got vector u. I've got vector v. And what I want to do is I want to create a vector w, okay? Here's the idea. I want to create w so that u dot w equals 0 and v dot w equals 0. I want a new vector. I'm just going to generically call it vector w. I want a vector w so that it is orthogonal simultaneously to both u and v at the same time. That would mean it's orthogonal to the plane they live on. Well, how would I do that? Well, actually, there's some algebra involved. I'm going to walk you through it. It's really not that complicated, and I don't know why this isn't in any textbook I have ever seen in my life. Never found this on the internet or on YouTube, but it seems like something everybody should know, especially if you're going to use them. So let's do the dot products. Oh, so that should be a W1. There we go. So I've got U1 W1 plus U2 W2 plus U3 W3 equals 0. And V1 W1 plus V2 W2 plus V3 W3 equals 0. I have two equations and I want to solve for W1, W2, and W3. Well, if you're in linear algebra, you might say, well, I can use a matrix and I can do all this stuff. It's only two equations. A matrix is fine, but it's probably overkill. So let's go back to baby algebra. How did you eliminate an unknown? I'm going to write down something. All of you have done this before. You know, you had 3x plus 2y equals 9, and you know, maybe 5x minus 6y equals -1, and I want to eliminate the x's. So what did we do? Well, we said, why don't I multiply the top equation by 5 and the bottom equation by maybe -3, and then when I add the equations, the x's will go, right? We call that the addition method. That's it. That was a very simple algebraic technique. Well, that's what I want to do here. In the first, I want to eliminate the W1. So if I want to eliminate the W1, probably the easiest way to do it, let me start by multiplying the top equation, okay? Let me multiply the top equation. How about by, which one do I want to do? I want to do the top equation by -V1 and the bottom equation by positive U1, okay? Then they will be able to cancel stuff. So if I do this one by -V1, I'll have -U1 V1 W1, -U2 V1 W2, -U3 V1 W3 equals 0. Here, I'm going to multiply this equation by U1, so I'll have positive U1 V1 W1 plus U1 V2 W2 plus U1 V3 W3 equals 0. So now when I add the equations, those two guys are going to cancel, okay? Now what am I left with? I'm left with this stuff W2, this stuff W3. So right now I'm left with U1 V2 minus U2 V1 all times W2 plus U1 V3 minus U3 V1 all times W3 equals 0. Well, let's throw this on the other side, and then we'd have U1 V2 minus U2 V1 W2 equals. Then it would be U3 V1 minus U1 V3 W3. Okay, well, the easiest way to do this, notice, if I choose W2 to be this, and I choose W3 to be this, then they will be equal. So I'm going to choose W2 to be U3 V1 minus U1 V3, and I will choose W3 to be, where is it? U1 V2, U1 V2 minus U2 V1. Okay. Okay, everybody got that so far? Now, if I do this again and I eliminate W2 or I eliminate W3, let's say I eliminate W2, I'm going to get the same thing for W3, but what I'm going to get for W1, I'm going to fast forward because I don't have the board space. In class, I would go ahead and do all of this. But if I do the exact same process that I just did, add and then eliminate, I would get the W1 is, oh, my hands are cramping. Oof, hang on. my hands keep cramping on me here. The W1 is going to be U2 V3 minus U3 V2. But you also notice something. W2, there were no 2's in here. W3, there were no 3's in here. And W1, there's no 1's in here. That's kind of an interesting thing. So we are going to define dot product to be the following. I'm now going to define it. And I'm going to show you that it works and why it works and how it works and how easy it is to actually perform. And then all the cool algebraic and, more importantly, geometric properties that it has. We are now going to define U cross V, and that's how we write it. We write it with a little x. Very different from dot product, okay? Hold on a minute. I'm going to run out of room here. Here, I'm going to write a little bit lower, sorry. It's long enough that I need a little bit more space. I'll put it right here. U cross V is defined now forevermore as U2 V3 minus U3 V2, comma, U3 V1 minus U1 V3, comma, U1 V2 minus U2 V1. This is the definition of cross product because we derived it by creating a vector that was mutually orthogonal to the first two. Now I'm going to prove that part too. That's actually quite simple. So here's what I'd like to do. This is a simple exercise, and this is something you should do every time you do a cross product. You should do the following thing. I'm creating a vector that I'm claiming to be orthogonal to the original vectors. The only way to know that I did it right is to actually now do the dot product of this with this and or this with this. And if I do it correctly, that dot product should produce 0. So let's do that right now. Let's just do one of them. Let's do U dotted with the quantity U cross V. If I do that, it'll be U1 times this, U2 times this, and so on. So I'll get U1 times U2 V3 minus U3 V2 plus U2 times U3 V1 minus U1 V3 plus U3 times U1 V2 minus U2 V1. Okay, hopefully I did this right. I'm going to keep them kind of in an order that I can easily read. So the first one's going to be U1 U2 V3 minus U1 U3 V2 plus U2 U3 V1 minus U1 U2 V3 plus U1 U3 V2 minus U2 U3 V1. Yikes, that's a lot of stuff. Well, let's see. This and this, those cancel. This and this, those cancel. Hey, and what do you know? Right, crowd goes wild, confetti everywhere. Yay, it worked. Yeah, it's supposed to work if I did it right. If I do V dotted with this, I'll get the same result. So what I've come up with is a vector that is orthogonal to both of the original two vectors at the same time. And that is really important. That is one of the main goals. That's not the only goal. But one of the main goals of cross product is to create this new vector. Again, it has to be in 3D. That's why it's orthogonal to the plane the other two guys live in. Now, where people have trouble is, how do I physically perform this process? Well, I am lazier than most human beings. I don't like spending a lot of time. And most people learn a technique that is really, really terrible. It's very long, and they usually get the wrong answer. And they try to take a determinant of vectors, which, first of all, mathematically, that's an impossible thing. You can't have vectors in a determinant. You can only have numbers. But they'll do this, and they still get the wrong answer, and they'll fill up 2 pages of writing. I'm going to show you something that you've never seen unless you were in another one of my classes. I want you to be right 100% of the time with the absolute least amount of effort humanly possible. How's that? Good goal. U2V3 minus U2V2. U3V1 minus U1V3. U1V2 minus U2V1. That's it. When I do cross product, it usually takes me about 10 seconds to do the entire problem if I'm taking my time. I can usually do a cross product in 5, 6, 7 seconds. Most people, it's like 5, 6, 7 minutes. And then they still get the wrong answer. I want to walk you through how ridiculously simple this is. Okay, most people have never seen this, and I don't know why. It's the easiest way to do it. So I have vector U, let's say, is -3, 4, 1. Vector V is 2, -1, 3. The trick is stack your vectors. Put one on top of the other, so you don't have to look around the page to find them. Check this out. 12 minus -1. 2 minus -9. 3 minus 6. That's it. Wouldn't matter how big my numbers are. It can't take longer than what I just did, ever. Now, is it possible I made an arithmetic mistake or a sign error? Yeah, we do it all the time. So how can I know that I did it right? Because this vector has to be orthogonal to these two. So I'll do a quick check. 26. I think I may have already moved it up. Let's see. 12, 13, 2, 1, 3. Oh, 3 minus 8, not 3 minus 6. There we go. I did booger it up. Okay. 26 plus -11 plus -15, that's 0. Or -39 plus 44 plus -5, that's also 0. That's my check. Every time you do a cross product, you should immediately check it by doing a dot product. And by the way, you don't need to do both of them, just do one of them. If your answer is correct, both dot products will be 0. If your answer is incorrect, then neither dot product will be 0. So you only have to check it once, but you should always check it because the check is the fastest part of the problem, doing that dot product. We'll do another one.
Professor, can you show the pattern that you take again?
Yeah, because that's the result. I had a student several years ago showed me, he figured it out using his fingers, and I pulled a muscle trying to, imitate him. No, that was a joke. He showed me, he goes, here's how he does it. He goes, this minus this, that minus that, that minus that, which is actually correct. That's what, let me walk you through it. You don't have to do very many to get the hang of it. So let's do another one. Vector U is 5, -7, 8. I'll make them a little bigger. Vector V is, how about 9, -6, 4. I'll erase this. So U cross V. -28 minus -48. So that would be +20. Now, I went that way, that way. Now I'm going to go this way, this way. So 72 minus 20. Now I'm going to go this way. Negative 30 minus negative 63. So that would be positive 33. Think I did that right? And then my quick check, 180 minus 312 plus 132. Yep, that is 0. So I did it right. Okay. The most important thing is that you got it right. Now, we have a vector. We have a new vector, and it's orthogonal to the plane that the original two vectors lived in. But now there's something about the magnitude that might be kind of important as well. Now, by the way, we proved last day that vector addition is commutative. I just proved when I did dot product that dot product was commutative. What about cross product? Do you think cross product's commutative?
No.
Why not? If I cross in the opposite direction, if I do V cross U, I'm going to get this minus this, this minus this, this minus this, aren't I? In other words, I'm going to get the negative. Oh, cross product is not commutative. What you get is a vector of the opposite sign. So all the numbers will be the same. It will be the opposite sign. So in this example here, if I done V cross U, it'd have been negative, negative, negative. Now, next thing is, I have two vectors. This is important. I want the cross product. Obviously, it's this one, or could it also be that one? Ooh, I'm going to put them this way. So obviously, it's that one, but wait a minute, couldn't it also be that one? Do you all agree that I really have two choices? Oh, this one, and then going in the opposite direction, that one. Hopefully, you all see that. I really have two choices. I have a plane. I would like a vector orthogonal to the plane. Obviously, it's right here, or is it right there? Question is, how do I know? Oh my gosh, how do I know? Well,
So will you have two answers?
no, because if I change the order, I get a vector in the exact opposite direction. So I'm saying every time you do a cross product, it feels like you have two choices, don't you? I mean, two possibilities. Well, did I do U cross V or did I do V cross U? So here's what I want you to think about. This is the X, this is the Y, this is the Z. Now, this is coming out of the board. Now, there's a very, very strict scientific method. Okay, my X is coming out of the board, my Y is going sideways, my Z is going up. So I want to do the X-axis, a vector on the X-axis, and I want to cross it with a vector on the Y-axis. Do you all agree that it should be pointing either up or down in the Z direction? Because this is the XY plane. I mean, Z is orthogonal to the XY plane. Does everyone see that easily? That my answer should point up or down?
Yes.
So if I'm going in the X direction, think 1, 0, 0, and I'm going to cross that with the guy in the Y direction, it's going to go up. But what if I go in the Y direction and I want to cross it in the X? I can't do that. So I'm in the Y direction and I want to cross it in the X direction. There's a really simple formal rule. Does everybody know what it is called?
The right-hand rule.
The right-hand rule, exactly. If I point my fingers in the direction of the first vector and I close my hand towards the vector in the second direction, my thumb will point in the direction of the cross product. Isn't that crazy? By the way, there's no left-hand rule. And by the way, I can't bend my fingers backwards. That's why if I reverse the order, I turn my hand over, that's why it will point in the opposite direction. So when I did this product, let's say I crossed it, that's what I got. But if I reverse the order, I think about turning your hand over. Using the X, Y, and Z axes is usually the easiest way to think when you're doing right-hand rule. Now, this has everything to do with direction. And there are so many practical issues here, it's unbelievable. Now, I'm going to give you a really simple example, okay? If you've ever changed your own tire, you got a flat tire, you jacked the car up, you got out your, your thing, and you're attacking the lug nuts. Hopefully they're not tightened too tight by the the tire place, and you're trying to do it. And probably everybody who's done this had this horrible thought at one point going, my God, nothing's moving. Am I actually tightening it? I mean, anybody who's changed their tires probably had that thought, oh my God, am I tightening it? Which way should I be turning it? Oh my goodness. Now, think about the rotational, okay? When you are tightening something, you can only turn it in one direction, clockwise. Because if I tighten something clockwise, my thumb's going to point in. That's tightening. But if I want to unscrew it, I've got to go counterclockwise because my thumb points out. And again, we have a very, very formal, really, really high-powered vocabulistic way of describing this. Anybody know what it's called?
Righty tighty.
Righty-tighty,
Lefty loose.
lefty-loosey. Although righty is kind of ambiguous because it's really clockwise. But when you tighten to the right, that's tightening. Why? That's cross product. It's a perfect example of cross product. When I have something and I'm screwing it on, like a lug nut, if I go clockwise, so we always think of the top, I'm turning the top to the right, I'm going to make it tighter. When I want to unscrew it, I got to turn the top to the left, unscrew it. But when you're trying to do it and you're using all your strength, a lot of times you're not thinking of that. And that's kind of mess you up. Righty-tighty, lefty-loosey is actually cross product. You didn't even realize that. And like I said, it's practical. Now, child safety cap. Okay. Hopefully your parents invested in those when you were young. You have something, might be medicine, might be something that you're not supposed to get into. What's the child safety cap? What's different about that?
You got to push down.
Yeah, it doesn't follow the righty-tighty, lefty-loose. It's reverse threaded. In other words, it defies common sense and things like that. Because when you're a kid, you're trying to open it up and you can't open it up because you got it right. When you're trying to unscrew, pushing is not the obvious. When you're trying to screw something in, you would push down on it. So there's a reverse threading going on here. That's the whole idea of the child safety cap. Again, it's using cross product. Isn't that crazy? The cross product is something as simple as putting on screwing on a cap or taking a cap off of something. So we know which way. Anytime, my mother comes over and says, can you open this jar of pickles? I know exactly what to do. I lean on the jar. I usually use my left hand, and then I turn it counterclockwise. I don't have to think about which way, but if I try to turn it clockwise, I'm just going to make it tighter and tighter and tighter. Okay, cool. So now that tells us the direction of the cross product. So now the question is, what about the magnitude? So I'm going to show you something because I'm not going to go through all the algebra right now. It's just, well, I do this in the classroom when I have 50 feet of board space. I don't have 50 feet of board space. So over here, let me go back to modules. I'm going to walk you through this because I go in great detail here. In the cross product, and after I define it, I then go through this part right here. Okay, I show you the algebra of cross product, and I'm going to only summarize it right here just because, again, I don't have the board space. But in the posted notes, I've got tremendous detail in front of you. It explains where every single number and every calculation comes from. This is really important that you understand all of this. I don't need you to do this. I need you to understand where all of this stuff is coming from. This beat right here in the middle can be a little bit gnarly. When I'm doing this in a classroom situation, I did it with dot product. That wasn't hard, and that still filled up a lot of the board. But I want to show you for cross product what actually happens. Okay. And again, I'm going to summarize because I've got the posted notes that actually has the algebra details. I don't need to show you the algebra details now. I'm hoping that you do look at the notes later. Okay? I don't want you to just take my word for it. I want you to understand where everything actually comes from. So, let me see if I can find it here. Oh, hang on one second. Hang on one second. I lost a page there. Okay. Essentially, if I take, I'm going back to vector U. and vector v that's awful too. And here's what I'm interested in. Okay, and we get u cross v. Okay, I'm starting with these three vectors, and now what I need are magnitudes. So if I individually find each of the following magnitudes, and again, this is what I did on the notes. Ultimately, I really want the magnitude of this guy here. Okay, so what I do is I show the relationship, first of all, in the notes, I show the relationship between the square of this. Now, if you take the magnitudes of all the other guys and you take the magnitudes of the dot products and everything else, you can see then this ends up equal. Again, I'm summarizing from the notes. And then it's, hold on, and it's minus, make sure I got everything. Remember, scalar, scalar, scalar. I'm not going to do the expansion, but if you actually did the magnitude, so it means you can square this quantity plus the square of this quantity plus the square of this quantity. Then you're going to do the dot product, which is this plus this plus this, and then you're going to square that trinomial. It ends up being really long-winded. Okay, again, I got that in the notes. I show you in the notes that the square of this magnitude is equal to the square of this minus the square of this. Now, in and of itself, that's not entirely useful, okay? Not yet. But what's this? Isn't u dot v length u, length v, cos theta? So this would be minus length u squared, length v squared, cos squared theta. Because I'm squaring length u, length v, cos. Okay, well, now I just made this even more complicated. Or did I? Can I factor this out? Yeah. So 1 minus cos squared. Oh, but wait a minute. What's 1 minus cos squared?
Sine squared.
Sine squared. This squared equals this. So what does that mean? That means we have an incredibly powerful and important result. That the magnitude of u cross v, now take the square root of the right side. Length u, length v, sine theta. Huh. Now remember, dot products can be negative. Okay, dot product can be negative, but the sine of the angle cannot. Why? Because theta is somewhere between 0 and 180 degrees. I mean, first and second quadrant, the sign is always positive. So positive, positive, positive. The exception would be if I have two vectors that are pointing in the same direction. Now, this is interesting. I have two vectors that are basically just multiples of each other. The question is, they don't uniquely determine a plane, do they? Ooh, so where is that other vector going? It seems like it can go in infinitely many directions and still be orthogonal. So instead, this vector has to be the zero vector. The zero vector is going to be the only vector that's orthogonal to those two. So if my angle is between them is 0, or if the angle between them is 180 degrees, then my cross product will yield the zero vector. Okay, and its length would therefore be 0. So the magnitude of the cross product turns out to be this really simple formula right here, which is really convenient. So the smaller the angle between my vectors, the shorter the vector of the cross product is. And in fact, if the angle between them is getting closer and closer and closer to 0, the cross product vector is getting closer to the 0 vector. The maximum cross product is going to occur when these are exactly right angles. That's the biggest the cross product can be, because when they're right angles, sine of 90 degrees is the biggest the sine can ever be. Okay. Now, I want to show you something geometrically, which is kind of cool, which is an interesting way of looking at this problem. Some of you may have seen this, and I'm not sure where you would have seen it, maybe in a trigonometry course, because we don't do any of this in calculus until now. I'm going to draw a parallelogram. Okay, that's supposed to be a parallelogram. It's not very good, I know. Okay, that's height, h. Does anyone remember what the area of a parallelogram is? I'll give you a hint. It's the same formula as the area of a rectangle. It's base times height. Okay, everybody got that? It's just base times height. So the area of this parallelogram is just the base times the height. Suppose I don't know the height. I gave you A, I gave you B, and I gave you theta. Then what's the height? Well, it's a SOHCAHTOA thing. Sine of theta is h over b. So h would be b sine theta. Everybody agree with that? So there's two ways. There's two ways to find the area of a parallelogram: base times height, or if I don't know the height, the product of the lengths of the legs times the sine of the angle. By the way, what if this turns out to be a right angle? Then this would be a rectangle. And sine theta would be 1, and a times b is just base times height. Okay, so it's consistent. So, okay, well, that's interesting. Well, why is this important, Mr. Brown? Okay, let me replace a with vector u. Let me replace b with vector v. If I have a vector u and a v, and I mentioned this last day, they uniquely determine a parallelogram, don't they? I just have to complete the picture. So this has magnitude u, this has magnitude v, and that would mean the area of my parallelogram is length u, length v, sine theta. I'm getting this overwhelming sense of deja vu. The magnitude of a cross product is equal to the area of the parallelogram that those two original vectors uniquely determine. You see, if I give you two vectors, it's easy to get the parallelogram. We'll do it this way. I just extend this one down to here, right? Parallel, 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 parallel. I make a parallelogram by just completing the picture, and the area of that parallelogram is equal to the magnitude of the cross product. That is one of the cooler geometric properties of vectors and cross products in general. Okay, everybody cool with that? Very powerful tool. But that incredibly powerful tool now allows me to do other things. Okay, so I want to define an operation that you may never have seen, but it'll be a common one. I have 2 points. Okay, I can be on the XY plane. I'll just start with a simple one, XY. We're really going to do this in 3D generally. But if I had, here's point, let's call it X1, Y1, and here's another point, X2, Y2. Okay, I know there's one line that passes through both of them. I don't want a line, I want a vector. I want to create a vector. And what vector do I want to create? I want to create one that starts here and ends here. I want that vector right there. But remember, all vectors are oriented at the origin. So when you describe a vector, it always starts at the origin in terms of its coordinates, these guys. So what would this vector be exactly? Well, what would the x value be? Wouldn't it be the difference in those x coordinates? And wouldn't the y be the difference in the y's? So if I call this point P and I call this point Q, we're going to call this vector PQ, and PQ will be the vector x2 minus x1 comma y2 minus y1. I'm creating a vector by taking the vector of differences. You do not subtract points. Mathematically, that has no meaning. You don't take one point and subtract another point. No, no, no. I'm taking a vector of the difference in coordinates. And this vector right here looks exactly like this, because it's now starting at the origin. Okay, now I can take a vector and move it all I want. Okay, but it's starting at the origin and it looks like this. So if I create a vector of point, I do this. Now, why would I ever do something this crazy? Because now I want you to think 3D for a moment.
I'm sorry. Is that a line segment or array you drew on the graph?
Vector.
But it's between 2 points, P and Q, correct?
Yeah, it's a vector. I'm creating a vector. I'm starting at one point and I'm ending at the other point. I want that particular vector. But remember, vectors are always oriented from the origin when you actually get the coordinates. So the way you create the vector. So let's do an example of this. This is how we're going to actually come up with equations of planes and things like that. Let's suppose I gave you, I'm going to keep it real generic here. I'm going to give you 3 points. P, and we'll call P x1, x2, x3. Q, oh, I'm sorry, not x1, sorry. I'll use x, y, z, sorry. x1, y1, z1, x2, y2, z2, and R, we'll call it x3, y3, z3. All right? There's 3 points in space right now, 3 distinct points. We know I've got 3 points in space. Those points live on one plane. If I give you 2 points in space, I'm holding them right here. If I give you 2 points in space, we know there's exactly one line that passes through them. If I give you 3 distinct points in space that are not on the same line, okay, they're not collinear. If I give you 3 points in space that are not on the same line, they uniquely describe a plane. Okay, so I give you 3 points in space, I can, get my plane and my plane that passes through all 3 points. Great. But how do I come up with that plane? Well, I'm giving you 3 points. What we do is we first create 2 vectors. I'm going to create 2 vectors. I'm going to create the vector that goes from P to Q, and I'm going to create the vector that goes from P to R. Okay, so I'm going to start by creating vector PQ, which will be the vector x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. And I'm going to create vector PR, which is x3 minus x1, comma, y3 minus y1, comma, z3 minus z1. Okay, I now have 2 vectors in space that are both oriented from the origin. I would like a vector that is orthogonal to the plane that these live on. How am I going to do that? I'm going to do PQ cross PR. That's what we just got done doing a few minutes ago. We're going to create a vector that is orthogonal to the plane that all 3 of these guys live on. Next day, we're going to learn how to actually find the equation of the plane. We're trying to first find the vector that's orthogonal to the plane. Okay? Now, I'm not orthogonal to points, I'm orthogonal to vectors. Okay, that's really important that we recognize that. So let's do a simple example of this. So let's suppose my P was -3, 0, 4. Q was 4, 1, 2. R is -5, 3, 6. Okay? Then PQ and PR are the following 2 vectors. PQ, 4 minus -3, that's 7. 1 minus 0, 2 minus 4. That's a vector in space now. PR, -5 minus -3, 3 minus 0, 6 minus 4. So then PQ cross PR. Now we have a name for this vector. The vector that is orthogonal to the plane that the other guys live on is called the normal vector, okay? Normal vector. And we often just write it as vector n. In vector situations, in this context, whenever you use the term normal, in this context, normal will have to do with orthogonal, okay? Like a normal vector to the basketball was orthogonal to the surface of the basketball. That's all that means. And this vector would be 2 minus -6, 4 minus 14, 21 minus -2. And I will do a quick check. -16, -30, plus 46, yes, that's 0. So this vector here is orthogonal to the plane that these 3 points move on. Kind of crazy, kind of cool. All right, got one more thing. Oh, good, we still have time. We got one more thing. Okay, I will open it up to questions in just a moment. So the last thing we want to do, and this one's really, really cool, that, I don't take credit for any of this stuff. Whoever figured this stuff out, a lot of it's just really cool geometry that people figured out long, long time ago in a galaxy far, far away, I think, something like that. All right. I have 3 points. Pretend we're in 3D. I have 3 points in space. Okay. We agree there's one line passing through P and Q. There's one line passing through P and R. There's one line passing through Q and R. Okay, cool. I would like to find the distance from point P through the line passing through Q and R. I want to find this distance. Now, one thing we know about distance, okay, when we're measuring the distance from a point to a line or a point to a plane, it's always the orthogonal distance. You see, I could draw infinitely many line segments from P to this line, but it's only the orthogonal. That's the one that represents distance, okay, the closest. So I want to find that distance. I'm giving you 3 points in space. Whew. Not a trivial thing. I mean, if I could even figure out the equation of the line and then using distance formula, and man, that would be a lot of work. So we're not going to do that. I want you to think cross product. What if instead you said, make a vector and make a vector? Okay, let me just make 2 vectors there. Now tell me, if I take vector QP, and by the way, it doesn't matter what order my points are in. I'm going to draw a picture and I'm going to make the formula fit the picture. I could have put R here. I could have put Q here. Okay, but I need this to go from here to here. If I do this, I know I'm going to get this vector coming out, right? Or going in the board. I'm going to get a vector. Okay, great. How does that help me? No, I don't want the vector. I want the magnitude of the vector. Anybody want to tell me what's the magnitude of that vector equal to? Isn't this magnitude equal to the area of this parallelogram? Let's call that height. I'm trying to find the height. But didn't we just say the area of a parallelogram is base times height? I'm trying to find the height. What's the base? Length QR. The area of this parallelogram I know is the length of the base times the height. I'm trying to find the height. So the answer to the question, how far is P from this, is simply and to me, that's so much easier. So this is a question I've asked you on the quiz. I'll say, here are 3 points in space. Find the distance from one point to the other 2, or the line passing through the other 2. Draw a picture first, okay? Because I might ask the question, how far is Q from the line passing through P and R? Or I might ask the question, how far is R from the line passing through Q and P? Here I said P from the line passing. It wouldn't matter how I asked the question. That's how we find the answer. It's magnitude of the cross product divided by the length of that base. That's it. Again, kind of interesting geometry. We're really far from calculus right now. We're not using any calculus. what we've got now is a well-defined operation called dot product and all of its ramifications and all of the things that come from it, particularly projection. Then we define something called cross product, and we look at all of its results, things like magnitudes of cross products, directions, okay? And we're eventually going to use that to create planes. That's next class. And so there's a lot of geometry still at stake here that has to do with cross product. And we're going to learn ways of doing things that are far more efficient than maybe other algebraic areas that you may have seen in the past, which is kind of nice. So I'm going to stop here.